Hello, everybody. This is an introduction to distributed computing. In this video, we are going to focus on DCOPs, distributed constraint optimization problems, and DSA, which is distributed stochastic algorithm for solving DCOPs. So what are DCOPs? To better understand that, we first need to look at an example. So let us have a look at the following. Here we see a military problem example. In this tactical example, we have an enemy unit entrenched at the top of the screen, and below it we have two ally units, infantry A and infantry B. Each infantry unit can do one of two things: charge or fire. The objective is to flank the enemy squad while sustaining minimal casualties to ally forces. To complete the problem setup, we are only missing our constraints. So let us show the constraints. As we can see here, if infantry A chooses to fire and infantry B chooses to fire, both sustain a lot of casualties. In the case infantry A and infantry B decide to charge, they also sustain a lot of casualties. But if infantry A decides to charge and infantry B decides to fire, no casualties are sustained because infantry A is decently close to enemy squad, and infantry B can offer fire cover. If infantry A decides to fire and infantry B decides to charge, a small amount of casualties is sustained because infantry B is decently far from enemy squad. We have different parts to our problem, so let's review them formally. We have an infantry unit that has to decide what action to adopt. The unit represents what is formally called a variable, and we denote it X. The mentioned action the infantry has to adapt must belong to a viable set of actions. This set of actions is called a domain, and we denote it D. Finally, in order to make the best decision, we must consult our constraints. We denote them C. To solve our problem, we need to choose an assignment for each variable from the variable's domain. Since we care to find a solution that is minimizing casualties, we are searching for an optimal solution, or at least striving for it. To find the best assignments, we will start with a random assignment. For example, both allied units will fire. Each unit will consult its constraint to get an idea of how good their assignment is relative to the assignments others have adopted. Each variable represented by an infantry unit will decide whether to change its assignment in order to optimize the desired solution. In our example, if infantry A changes to charge, the result improves. Therefore, infantry A changes assignment. It is also true for infantry B. Oops, we're stuck in a cycle. When infantry A changes an assignment, so does infantry B, and vice versa. And so they both stay on the same page. How can we solve this? Well, we choose a probability from transition withholding, meaning every now and then a variable will maintain its assignment even though in its perspective it might not seem beneficial. That makes our algorithm explore the problem space and potentially fire desirable solutions. So, when are distributed algorithms like DSA useful? Let's look at a use case to demonstrate distributed computation and the use of DSA. Here we have a battle scenario, multiple units scattered near multiple threats. Suppose we have a battle commander with a tactical command and control station, and their computer can run some algorithm to assign units to threats optimally. The battle commander is an obvious threat to the enemy for multiple reasons, especially due to command and control abilities. Enemy efforts are concentrated on destroying the tactical advantage, and once the command and control unit is destroyed, our ability to assign units to threats in a manner that is better than random assignment is lost. With DSA, or distributed algorithms, that is not the case. All units on the battlefield are processing units. They're independent. Even if a unit is lost, DSA can keep running with the remaining units. To summarize, we have covered DSA and distributed computing in this video. We've talked about one of the advantages of distributed computing and covered the main concepts and formalizations of distributed constraint optimization problems. Now that we have a basic understanding of the theory, we can start tackling the practical aspect of the matter.